Welcome, everyone. Thank you for coming to Building for Trust. Hope you're enjoying the last few hours of GCP Next this year. My co-presenter, Jess Frazelle, and I are going to talk about how to run containers securely using Google Container Engine. So before I introduce her and she introduces me, I thought I'd mention the context that we're going to assume you have. If this is your first time hearing about Kubernetes and you don't know about containers, this talk may be a little too high level for you. You can either find something else to go listen to or just follow along as best you can. So we are going to assume you have general knowledge of some of these things. My co-presenter here is Jess Frazelle. She's on the Google Container Engine security team and also works on Kubernetes. She recently drove a lot of the process improvements for doing security vulnerabilities and disclosure and patching that. Before she joined Google, she was working on Docker itself and was involved in a lot of the Linux security module support in that system. Jess.
I'll introduce Alex Mohr, my coworker and the technical lead and manager of some of the Google Container Engine teams, including platform security. For 2.5 years, he's worked on GKE, and then before that, he worked on the Google Compute Engine. So what we're going to cover today is like a basic outline is security boundaries, identity and access management, runtime security, and a demo, and then the Kubernetes roadmap for the future. So let's just dive right into the security boundaries. We have these various security models. The way it works today is single tenant. There's one trust boundary, which is your entire cluster, and all users are admin. But with some features coming in Kubernetes 1.6, including role-based authentication, which we'll cover more in depth later, we are moving into a different model where single tenant multiple identities, there's multiple users, no really enforcement, but you still treat the entire cluster as your boundary. So as long as you create multiple clusters for various projects or teams that you don't trust to be on the same one, then you're totally fine. And of course, spinning up clusters in GKE is super easy, like command line tools, or you can use the UI. And then we'll move into a more cooperative soft multi-tenancy where this is more multi-user, fine-grained authorization permissions. It's not entirely fully hardened, but it's good enough for multi-tenancy inside the same company. You can control bad actors and remove them from the cluster. So what this single tenant kind of looks like is you have your entire cluster as the boundary. Team 1 and Team 2, you trust to be on the same cluster, so you put them there. Otherwise, you'd have a new cluster for whoever that is. And so you have their front-end apps and their databases running on the same cluster as each other. All the nodes have the same authenticated identity. All pods have the same authorization permissions. And all pods have network access. So now I'll pass it back to Alex to cover identity and access management.
Thank you, Jess. So let's talk about identity and access management. The first part of this is authentication. That is, who are you? We'll talk in a little bit about authorization. What can you do? So user authentication, who are you? If you are the little puppet in the upper right corner there, you want to access a GKE cluster. One way of doing that is using bearer tokens, and another way of doing that with Container Engine is that you can use Google OAuth 2 access tokens. So for example, if you run that line on the top after you've authenticated with Google using gcloud auth login, you can go get credentials for a given cluster, and that will configure your kubectl config file such that it will use those credentials when accessing your cluster. When you then issue your kubectl create command, passing in some YAML file that you want to have created, then what will happen is your request will be sent to the GKE cluster, the API server that's hosted for you, and it will receive that request. The Google OAuth 2 tokens will be included in there, and those will then be forwarded to GCP's IAM service to verify them. If that happens, then the response is passed back to the API server that runs on your cluster, and you'll then be authenticated as your identity. Users are not the only identity that we care about. We also have many system components. So a Kubernetes cluster is not just a single thing. We have the GKE master, which has controllers and API servers and many other bits. But your cluster also consists of the nodes that are participating in it. So the master itself has a certificate authority, one CA for the entire cluster. And the master is then given certificates that are signed by that CA. At the same time, the nodes in the cluster are also given node certificates and keys that are also signed by that same CA. And when we create these nodes on your behalf, we pass along the details of what those node certificates are in the VM metadata server that these nodes are running on. And so then the nodes are able to fetch that key and that cert down from the metadata server, and when they contact the master, then you get mutual authentication. So the nodes are going to verify the master cert when they're talking to it to make sure that it's really the master that they expect it to be. And of course, at the same time, then the master can verify that the node is coming with a cert that is signed by that CA, and therefore it should be allowed to join the cluster. And this is important to stop nodes that you do not want to be part of your cluster from joining it. The third pillar of authentication we have is for workloads. So Kubernetes has support for the things running inside your cluster to also have identities. So maybe you want to have a cron job style service that runs inside your cluster, and your cron job is going to do something every hour, like contact the API server to create a particular pod or a deployment, a replica set, whatever it wants to do every hour. And in that case, the thing that's running in my cluster needs to have some form of mechanism for identifying itself to that API server so it will have permissions to do what it wants to do. So there are two parts to this. On the left, you can see we have Kubernetes service accounts. And the way these are implemented is that there's a service account controller that runs, and it signs any JOTs for all of the service accounts in the system. So if there's a service account, a JOT will be created for it. And those JOTs then get stored in the API as secrets. And so then when you want to create something that uses a given service account, you can specify for your pod, please use specified service account. And if you don't specify a service account, currently the default is that you will inherit the namespace's default service account. And currently that namespace's default service account usually gives you full access to the cluster. So once your pod is running, it has this access to the secret, and the secret will be then mounted at a known location in the pod's file system. And so when you want to make your request to the API server, your pods can then read in that JOT. They can use it as a bearer token, and they make that request to the Kubernetes API server, and therefore they will be authenticated. And of course, the API server will allow you to do that. So again, if you wanted a cron job or anything along those lines, maybe you have a third-party resource that you want to extend the API server with, you can do that, and the service accounts provide you a mechanism for doing that without having long-lived bearer credentials that are outside of this system. So that's authentication. Let's talk about authorization. So given your identity, or an identity, what can you do with it? Today, Kubernetes supports what's called, at least called in Kubernetes, ABAC, Attribute-Based Access Control. This is really just a very simple file-based authorization policy. If you're running Kubernetes yourself, you could configure it with more details, but with Container Engine today, it's a static file that basically supports only an admin identity. What we'd like to do is offer people more fine-grained access control than that. And so what we've been doing is working with some of the people in the community to get roles-based access control, which is another authorization mechanism that the Kubernetes API server will support. And this is going to allow for much fine-grained authorization. And you can also configure it using the Kubernetes API itself. So the configuration mechanism is through the API. You can create, I'll talk a little bit more about that in a minute, roles and role bindings and so on. And so that'll give you full control to configure the permissions in your cluster. So what is the basic usage of RBAC? If you look on the left there, we have one of the resource types on Kubernetes is a pod that might contain multiple containers. And the API server supports two access mechanisms. You can call get on the pod, and maybe you can call list on a pod. There are also a whole bunch more like create and delete, but for this simple example, we'll just focus on list and get. And maybe on the far right up there, I've got the user in blue, and I want to be able to say, hey, this user should be able to call get on pods. They should be able to list the pods in the system. So how am I going to do that with RBAC? The first step is to create a role. That's the gray box. We might create a pod reader role. And this basically says anyone who's a member of the pod reader role has that capability. They can call get on pods, they can call list on pods, and life will be good. So I then need the final piece of this is a role binding. That's the green box, which says this particular user is bound to this particular role. If they have authenticated themselves as this particular user, they have this role available to them. And so when the user comes in, the authorization system looks and says, OK, you're Alex Mohr at google.com. Look at those roles. Yes, you do have the pod reader role. There's a binding there between them. You're trying to call pod.get. No problem. Everything succeeds. So that's the basic usage. RBAC supports a lot more complexity. Even in this case, if you said, well, what if I have nodes as well? Maybe I want to have, in the bottom gray box over there, a node pod reader role. And that might allow anyone with that role to be able to both list pods as well as get and list on nodes. And the bindings in this case also can be extended. They don't just have to be plain users. When your users are authenticated, they may come with a set of groups associated with them. So if you're authenticated as Mohr at google.com, and maybe I'm in a group, cluster admins, then the cluster admin group could be given the node pod reader role. And it's also not limited just to users and groups, of course, but service accounts can also be part of these things. And although I don't cover it in the slides here, there are many more forms of this limited to namespaces. There are cluster roles and so on. So it's a pretty decent authorization system that gives you a lot of control if you'd like to use it. There we go. So the third pillar of IAM, we have authentication, authorization. The third A is often referred to as auditing. So right now, the GKE cluster API is integrated with GCP audit logging. It's currently in beta. And we currently support the admin activity form of this for cluster modifications. So if you're going to create a cluster, you're going to upgrade a cluster, maybe you're going to change the node pools in a cluster, you're going to delete a cluster, all of those kinds of admin write actions are going to be reflected in an audit log. And so it's more or less what you would expect in simple form. Alice at example.com created cluster foo. A few lines later, Joe at example.com deleted the cluster bar. The details in here include all of the request information. They include the response that we send back. They include the identity that did it, timestamp, cluster IP, pretty rich set of metadata about each of these requests. And those are then sent to Stackdriver logging, so you can go and use any of the standard Stackdriver logging APIs to go look through that. And of course, the Google Cloud Console also offers a relatively nice overview where you can see via the UI what's been going on in your clusters. Drill downs and so on also available. On the bottom, data access. This is a very commonly requested feature. We're starting to see more and more of Google Cloud Platform products include data access. This would be a log of all of the read operations being done. So if somebody is calling a list node pools or something like get cluster credentials, those are the kinds of things you might expect to see in the data access logs. And then finally, in this section, I wanted to talk briefly about secrets. So the previous section was talking about authorizing to the Kubernetes cluster itself. What if I need to do something like access a database, and I need a password for that database, a username password combo? Or what if I want to make calls to GitHub and its API? Maybe I need an access token in order to do that. So secrets are a really nice Kubernetes feature that allow you to do that. You can store other static credentials having nothing to do with Kubernetes in those secrets. You can then use pod's YAML in order to reference these secrets. And then when you actually have these secrets in your pod, you can access them via a file mount or an environment variable. And you can configure how they get exposed to your app that runs. One of the nice things about file mounts is that if you change your secrets, eventually the file mount will also be updated to do it. So if you have anything that is rotating these things over time, you can just continually update the secret, and then based on polling intervals and time to lives on the kubelets, your app, as long as it's going to be polling its file mount on a regular basis, should pick up those changes as they happen. So to give you a brief example of how that works, and the code snippet on the upper right, you can see that the username in this case is admin, and Kubernetes YAML does base64 encoding for these. So that's the YWR string. Maybe we have a fun password like 1F, 2D, etc. That's also base64 encoded. And so in order to specify the secret, we specify the API version, the kind, metadata, give it a name, my secret. And then we pass in the data as a username and password field. So that's all for IAM for now. I'm going to pass it back to Jess, who's going to talk about runtime security and give us a really neat demo.
Sweet. Yeah, so runtime security, yay, containers. So I just wanted to briefly cover the isolation kind of primitives that make up containers themselves. So if you don't know already, containers aren't real things. Like when you create a container, it's not like actually creating this thing that's called a container. It's using Linux primitives that are namespaces and cgroups to do this. Namespaces control what a process can see, and cgroups control what a process can use, which is like the very clear distinction between the two. So as far as namespaces goes, there's a bunch that you can use. You can control what processes are being seen, mounts, networks. UTS is host name. IPC is like messaging queues. User namespaces creates a unprivileged user if you want, and it will be mapped to a different user on your actual host. And then there's also a cgroup namespace, just to confuse everyone, which controls what cgroups you can actually see. As far as cgroups go, you can control things like how much memory will be used, CPU. You can set a container to run on a specific CPU set. So if you want it to run on like 0 or 1, you can do that. You can control what devices are being used, network priority, freezing processes and threads, and block I/O, so writing to disk bandwidth and stuff like that. So there's really a lot of like leverage for you to kind of take the groundwork here and then build on top of them with more hardening aspects of Linux, which we'll cover now. So one of these is AppArmor, and this is a Linux security module. This is super helpful for creating profiles that will define what your process wants to write to, so you can set certain files as read-only without setting the entire mount as read-only, which is insanely helpful because read-only file systems are great, but it's very hard to make an actual application run entirely as read-only. You're going to need to write to something. So AppArmor is great for that. You can also deny system functions like mount, netraw, stuff like that. It doesn't cover all system functions. There's only just like a small subset. And we're going to push towards like sane defaults here. Docker has a sane default that prevents writing to proc, prevents writing to sys, all the things that you should not be doing regardless, unless you are running as a privileged container, and preventing mount. So this is beta in Kubernetes. And if you want to use it, you can do the following and create an annotation for your container that points to this. And what we're doing here is using runtime default, which will then use the Docker default profile for your basic Nginx container that we have here. So moving on, another one of these is Seccomp. And Seccomp gives you more leverage over all of the syscalls. So AppArmor, you could do a few like mount, but Seccomp, you can define like a whitelist or a blacklist of syscalls that your application is going to use. So in Docker, there is a whitelist, and it has some really sane defaults. When we were working on writing it, I went through all the past CVEs that were super bad, and we block things like ptrace and cloning new unprivileged namespaces, which has like the highest CVE rate for breaking out of containers. Things that if your application is not running as privileged, you probably don't need anyways. So for like 95% of the use cases, it works out of the box, which is great. So this is alpha in Kubernetes. So if you want to use this, it's kind of the same thing as before. You set the annotation on your container. And for this one, we're using Docker default profile. So there's a bunch of other things that you can set as well. You can set SELinux context for labels on volumes that you have in your containers. You can run all your containers in a pod as a non-root user or ensure that that's happening. You can set a read-only root file system, which, like I said, if that's impossible for your application, you can actually define granularly these things in AppArmor profile instead. And then you can also add or drop capabilities to your containers if you do not need them. So what this looks like if you want to say drop net raw, which really isn't all that useful unless you want to use ping. You could do this in the security context for each container, and then you can also set, SELinux options and labels, like I said, on your containers. You can define that you want it to be a read-only root file system, and you can also make sure that all containers are running as a non-root user. So now we're going to do a demo and switch to the other computer. Cool. OK, so this will be fun. So I have like a GKE cluster that I spun up that's running in alpha mode so that we can use Seccomp. So you could do the same if you want. So we'll just get another terminal since this one's dead. And cool. Well, that was fun. So we'll just show that there are no pods currently running. Fresh cluster, cool. So now we can have our way with this. So I have, first off, this one pod that we're going to spin up. That is cool. So if we look at our first pod, it's going to create 5 replicas. If we look here, it's just a simple app named Echo, which spins up Nginx. And Nginx just echoes out a bunch of header information and the body of the request. And it's just a stupid demo app. Then we have our Nginx configs, and we're exposing port 80. And we're not doing anything in this example with annotations and Seccomp. I just want to show that we can do things that we should not be able to do. So we'll spin this one up with a kubectl create. Right, so we'll just see that our pods are running. And I'll just grab one of these random ones, and we can exec in. And then I'll set the container as echo, and we'll run bash. So now we're in. Hacker voice, just kidding. So I'm going to try to do something that if this was running an Nginx container and I was actually escaped the application, if I tried to unshare something like a user namespace to break out, we would not want this to happen. But of course, it works because nothing's being blocked. I'm not running with any Seccomp, and kind of blows. So that's without Seccomp. If we look at this other one that I have that actually does add a Seccomp profile, it's the exact same as our Echo application. This one I just named Nginx. There's 5 replicas, again, because it's cluster. Might as well use it. And we're setting Docker default as our Seccomp profile. So by default, we know, since I wrote it, that unsharing a new user namespace is going to be blocked. So let's just verify that by spinning this up with another kubectl create. We'll make sure that these are up. And then I'll just grab another one of these randomly, and we'll exec in. The container name is Nginx, and bash again. So now we'll unshare and be evil, and it's denied. So that just basically verifies that it works, but that was no fun, basically. So let's kind of go into a more real-world example here of trying to stop a bad person. So I have another cluster here that I'm going to switch to. And on this cluster, it just so happens that sysadmin me forgot to upgrade one of the nodes after the dirty cow vulnerability. So the interesting thing about dirty cow, if you all didn't know, when I first heard about it, what I do with these types of vulnerabilities is I'll try and make sure that the Docker Seccomp profile kind of either prevents it or that we can edit it in such a way that it will be prevented for everyone that uses it. So when I first heard about Dirty Cow, I was like, crap. That one's not actually prevented by the default because it's using madvise. It's using literally nothing bad. You're just writing to a read-only memory map and using all the syscalls that people use daily, which is hard. But what I did know was that it needed, if we look here, you needed madvise and you needed madvise don't need. So I was thinking to myself, let's just not allow that. We'll allow everything of madvise, but not madvise don't need. So I had this patch ready to send when the vulnerability was going to be publicly disclosed, and I was just waiting on it. And it turns out, actually, and realized this before the patch was made, which was good, glibc malloc uses madvise don't need literally all the time. So that would break almost all applications by default. It could not be a default for anyone. So this one is very troublesome. So if sysadmin me is thinking about my cluster and for some reason we don't use glibc for any of it, I could be OK, I'm going to, for the time being, before I upgrade all the nodes and before I realize if we've been affected by this or anyone got in, I'm going to deploy all these pods with this custom Seccomp profile like I showed that takes madvise don't need. It allows literally all of madvise, but madvise don't need. So the order of operations I'm going to show these is in a specific order because after I pwn the node, then I can't spin up more containers on it. So we're first going to show blocking it. So sysadmin me takes my pod spec here, and I'm going to use this custom profile that I put. So it's basically a fork of the default that adds that. And I'm going to run this pop container, which basically tries to exploit the Dirty Cow vulnerability. And since I labeled my nodes, which in real life the system probably didn't, but I did for the sake of this demo to make sure it goes on the bad node, this is going to run on the Dirty Cow node. So if we spin this one up, and now let's get our pods. Cool. So let's grab this one and get some logs. OK, so it tried to pwn the machine, and it was could not pwn, and now our sad hacker is sad, which is great. So we prevented that. It gave the sysadmin time to upgrade stuff or assess if we had been affected, which is cool. So another sysadmin comes along, maybe also me, and forgets, to do this. Forgets to add the Seccomp profile. Forgets to even write the Seccomp profile. Just does not care. So we have another one of these where it's going to run on Dirty Cow. It's going to run the same exact container pop, and we're not going to have any Seccomp. I had to do this 1 second because the node just literally will not respond after this. So let's delete the old. And now we'll create the new. And now let's get our pods. Cool. And now we'll grab the logs from this one. And so game over, we could write to this read-only memory map. We had all these madvise calls, just totally killing the node itself. So that's the sad story. And then also, just for fun, we can spin up one of these on the non-Dirty Cow node, and I'll show you that it also doesn't work, just to verify that I'm not completely fooling you all. So if we delete the old, create the new. We'll grab one of these again, and our sad hacker is going to be sad again. Cool. So now if we switch back to the slides, basically what we learned is that you can run custom profiles. You can stop bad things from happening if you know that they're there. Usually the default Docker profile would block these things. There's actually a page that I wrote in the Docker repo that has like 20 plus vulnerabilities that were stopped by the default profile, but this was just a fun example for something that was not. And in other cases, I would try, like I said, to modify the profile without breaking everyone, which in this case it could not be. So the cool thing about this is that in GKE, if you run with opt-in for automatic upgrades for GKE node pools, this would never happen because we control the OS for all the nodes. So that's definitely something you should think about because we know about these things. We upgrade the nodes for you, and then you don't even have to worry, like, did I miss a node? Do I need to do some sort of custom profile? All that. It's pretty great. And other great features of like the OS that we use are it's a super minimal base. Really, everything has to be run in containers. There's a firewall that drops all network connections except for SSH by default. It's the default node image for all of GKE, and it's based off Chrome OS, which has really been like tried and tested as a great security operating system. The entire file system is mounted as read-only, and then certain file mounts are remounted again as like varlib docker needs to be executable and writable, and your home and var and a stateful partition mount can hold persisted state over time, but that's like literally it. So super great that GKE could possibly never have this happen. Now I'm going to pass it back to Alex to cover the roadmap for the future.
Thank you, Jess. Oh, yeah. So for the last section, I'd like to talk a little bit about the Kubernetes security roadmap. Full disclaimer, this is an open source project, and Google Container Engine inherits whatever Kubernetes upstream does. We obviously don't control it, so these are somewhat speculative future directions. We're looking, many people of the community share these goals, but there's no guarantee as to what the future will bring, of course. So two parts to this. First, I'm going to talk about some of the more long-term goals that we have, the problems that we'd like to solve, and then the second half of this, I'll talk about what we might expect to land with Kubernetes 1.6, 1.7, 1.8 over the next 6 months. So we talked a little bit about security model and stages. Jess gave us a nice introduction to single tenant with multiple identities, and then this notion of cooperative soft multi-tenancy. What we'd like to see, though, is hard multi-tenancy over time. So this would be where those security boundaries between the multiple tenants of a cluster become much more strongly enforced. And I'll talk a little bit about that in a moment. We might also want to see things like better resource isolation. If I have two containers running in different processes on the same machine, maybe one of them ends up trashing my L2 cache, and that causes the other one to run more slowly. So there are some interesting things in terms of looking at cycles per instruction that you might want to do in terms of trying to get better resource isolation between these different systems. If you want to think about like what would that maybe look like, we'll know that we've met the hard multi-tenancy goal if you were a provider and you said, yeah, I'm happy to have somebody from company A give me some code, whatever it is, and I'll run it, and company B gives me some other code and we'll run it, and they're running on the same system, the same cluster, the same nodes. So if you had hard multi-tenancy, it's really about this hard isolation. And just because you don't necessarily want to run third-party code from multiple companies, this might also be useful to you inside your organization. Maybe you have multiple different departments, maybe you have multiple teams. This kind of thing might also help in that case. So Jess talked to us about a cluster and the project as a security boundary and gave you this slide that you saw earlier. We'd like to change this. Instead of everything being the same authenticated identity, the pods having the same permissions, what we'd like to see instead is something where the namespace and pod become much more of a boundary than they are today. So this would mean things like the authorization permissions could be granted at a namespace resource level. So if we look at the example here, you might see Team 1 has a namespace, and they're running their front ends in red, their databases are in yellow. Maybe there's another team, team 2, they've got their own setup with front ends and databases shown below in blue and green. And the 3 nodes here are hosting the same pods as before, but now we have better notions of separation between them. In this case, maybe the nodes have their individual identities and per-node permissions. The pods have identity with fine-grained permissions. And we could even maybe think about how the pods could have limited network access to just whatever's necessary for them. So let's walk through these 4 things and talk about the user scenarios that those would reflect. So authorization permissions at the namespace resource level. So we'd like to move that to the per namespace per resource permissions. Today, everything has root in cluster. And that means that cluster is a boundary. Instead, what we'd like to do is take advantage of this security principle, least privilege, should be familiar to many people in security, right? And so the users and the system should have the least privilege possible, also the workloads. So for example, if one user of the cluster is Alice, she would like to be able, we want to make sure that she can list the the engineering services because she's a member of that team, but she shouldn't be able to go and pull down HR profiles, offer letters, things like that. Maybe Bob can create things in the test namespace because he's a member of the testing team, but he shouldn't be able to access things in prod unless he's a member of your on-call rotation, for example. Or maybe your scheduler needs to be able to know what the state of the nodes are and the state of the pods are in the system, but there's really no need for your scheduler to be able to read your HTTPS certificates, so it should not be able to read the secrets file. As far as the nodes go, we'd like to move them to have per-node identity and per-node permissions. So right now, each of your nodes can read any of the secrets in your system. They can read any of the pods in the system. That's OK for today, but we'd like to really move this to the least privilege model. So in this case, some example might be if I have a node, it should only be able to read data about pods that are scheduled on that node. If a pod is running on some other node in the system, there's really no need for it to be able to read that. Similarly, it should be able to read secrets for the things running on itself, but it shouldn't be able to read secrets for things that it doesn't need to know about. And if we get to this point, then a compromised node will not allow any additional escalation through the Kubernetes API. You'll be able to access things that happen to live on that node, but if there are 500 other nodes in your system, it won't be able to do things that reflect on them. Third, we would like pods to have their own identity and permissions. So as I mentioned now, if you have a default service account, the default service account has full admin capability on the cluster. Instead, we would like to move to a model where you have to actively grant workloads permissions. So if you want to create your cron job, it would be reasonable to say, yes, my cron job should be able to create pods in the system. Or yes, whatever my other extension is that's going to collect statistics about the things running on the system and create a dashboard that lets me do some amount of visualization, it should also be able to have these things. But if it's just your Nginx running on your cluster, Nginx really should not be able to go and delete all of your pods, your deployments, and so on. Similarly, if you have namespaces, if you're running a pod in one particular namespace, maybe it can access things within that localized namespace, but other namespaces that are isolated from it, it should not be able to have access to. And then fourth, network policy. So we'd like to move from all workloads receiving traffic from anywhere on the network to having network connectivity controllable by policy. So this case would be where you have a front-end system, maybe a back-end system. The front end should be able to talk to the back ends, but the front ends maybe shouldn't be able to talk to each other. And maybe your front end shouldn't be able to go out to the public internet and do other things. And we have some basic support for network policy right now. It requires some external plugins, and so we're going to iterate on that over time. I also want to talk a little bit about a couple of other features. So Jess talked about AppArmor and Seccomp and SELinux. We would like to have support for more security contexts. So no new privileges is a particular Linux flag, and it carries over between fork and clone and execve. And what it does is it stops new privileges from being added to a process. So that way, even if the initial process can't do something, it can't then create some separate process, give that other process more permissions, and then compromise your system that way. Another example of the kinds of things we hear about is binary verification. So today, Kubernetes supports an image policy webhook. So that, for example, every time a request comes in to create a pod to run a container, it'll take that image and pass it off to the image policy service, which can come back with image allowed or image denied. We'd like to expand on that basic support that's there and add audit logging for the image policy check so that you can have a full trail of what images were allowed, who was trying to create them. And if you have support for break glass, it's a production emergency, please just run it, ignore that it's not signed, make sure that that gets logged as well. And so that way you can do forensics afterwards and do to figure out what happened on your cluster. We've also had some people talk about binary verification of Kubernetes and its add-ons. So we're shipping all of these official containers. Right now, they do not have any attestation as to whether they're the right container or system or not. And so one of the things that might come over time is allowing the Kubernetes itself to verify those containers that it's running for its controllers, the kube proxy, the DNS, the kubelet, and so on, and make sure that it only runs fully verified system components if that's something you'd like to have happen. So with that, I'm going to switch gears to our last little section here, Kubernetes 1.6. I'll talk about the next releases after that. So we expect that to be released in open source towards the end of March. Google Container Engine should start picking it up and making it available shortly thereafter. And then over time, once we've verified that it's as stable as we hope it to be, we would then do the automatic upgrades to that version for any existing clusters. So as far as security model goes, we'll have a single tenant with identities and the beginnings of soft multi-tenancy. And pods should not have root on the cluster by default. Some of the highlights is that we're getting this RBAC system. That's been some of the main focus over the last 3 months, getting that enabled by default and giving people those richer capabilities to control their system. We've also been adding a lot of identities to the infrastructure components, the nodes, the controllers, and so on. And many of them have more limited permissions than they do with 1.5 and below, but not all of them. So Kubernetes is on a 3-month release cycle. So coming in June 2017, near the end of that month, we expect Kubernetes 1.7 to ship. As far as the security model for that goes, it should be a pretty decent soft multi-tenancy. And in particular, if you are able to escape a container, that escalation should be limited to just the one node that it's running on. So some of the highlights from a security perspective that we might expect to see are finishing the limiting enforcement of system components such that each particular node can only do what it wants to do, what it needs to do. We expect our audit logging to get much more comprehensive to include many more sources of what's going on in the cluster, and possibly also have capabilities to ship those. Right now, it's written to a file on the master itself, ship those off to network endpoints. And then we also hear a lot about certificate rotation, being able to take those certificates in your system and rotate them over time. There's more speculative bits, things like improved secrets management. Right now, the secrets are written to etcd as a database, and they're stored in plain text. On Container Engine, the disk itself is encrypted at rest. So we do have some amount of encryption at rest for GKE, but in Kubernetes itself, they're in plain text and etcd. So you really need to make sure that people can't just read your etcd database. There's also talk about runtime isolation improvements. So you saw how good Seccomp could be. We'd like to see that maybe become the default in Kubernetes and require people to say, no, I have something that is going to require extra special sys calls, and I'm going to trust it to do that. Give you this pod permissions to do those extra things. Once we've done all that, 3 months later again, September 2017, that's when we expect Kubernetes 1.8 to land. And at that point, our security model is starting what will probably be a long road to hard multi-tenancy. Unclear at this point. We're not looking forward quite that far yet. We're still in the 1.6 shipping phase and starting to plan for 1.7. Some of the things that we might see are VM-based runtimes via the container runtime interface. That would provide an extra layer of defense in depth. More binary verification, potentially that better resource isolation between containers that I mentioned. And then also large organizations might like to be able to specify policy. Everyone in my org should run with read-only file systems. You can't create a pod in my service that has that flag disabled, unless, of course, you're in the special whitelist. And so to give you a brief recap, we talked about 4 things: security boundaries, we talked about identity and access management, the runtime security and Jess's demo, and then a little bit of the roadmap for Kubernetes security. So with that, I'd like to invite people to come up to the 2 mics for questions. If anyone wants to chat privately afterwards, as privately as you can here, we'll go outside if we run over time, and you can meet us in the hallway.